Good day everyone. Today I'll be showing you more examples for our module 4 machine learning. This is the UCI machine learning repository website. So there are numerous data sets on this website that you can download to try it your own. So there are some real world examples as well as some simulated examples. So in particular, this data set is called the breast cancer Wisconsin data set. So this is an actual data set, and I think it'll be interesting, and it's also important to see how we can apply what we have learned on this data set. So this data set consists of, as you can see here, 569 instances. That means 569 rows, and we have 32 attributes, which means columns. And you can read about the information here and the attribute information. So we have one column, which is the ID number. So almost always the ID number does not contribute to any useful information, or we won't be using the ID number to predict or to infer the output. And column 2 of our data set is diagnosis, either it's malignant or benign. So since we are dealing with breast cancer data set, so this will indicate whether the patient has cancer or not. So you should know the difference between malignant and benign. And from column 3 to 32 are real valued features that are computed for each cell nucleus. So if we can read a bit here, it says features are computed from a digitized image of a fine needle aspirate of a breast mass. They describe characteristics of the cell nuclei present in the image. So from images of patients, various patients with either breast cancer or without breast cancer, they extract features and they produced this data set. So obviously this is, if we are interested in predicting an output, and the output should be either malignant or benign given this inputs, so this will be a classification problem. And if you are not interested in predicting an output, perhaps you can only use this inputs for unsupervised machine learning problem to see how these classes fit in. So we have seen one example on that. You can try it your own here as well. So I have downloaded the data set. You can go somewhere here to download the data set, and it's just a text file. It says data file. So if you double click, you can see that this is how it looks like. Okay. Of course, you can open this using Excel and it'll be displayed nicely. So you can see here, this is the ID number. And this is the class, either is malignant or benign. And these are the features. Now let's see our Spider IDE. So we'll be building some models here. So in particular, we'll be building the decision tree model. We'll be building the k nearest neighbor model and the logistic regression model. And we are interested in prediction. And as I said earlier, this is a classification problem if we want to predict. So this line would read the file wdbc.data. Let's go again. You see here wdbc.data, and I'm extracting the inputs and target. Our target is, if we look at data, let me just run this quickly. Data, let's see what is data. Data is the whole data set, and this is how it looks like. Our columns are not named properly, but we can see that this is just an index. This is my the class, either malignant or benign of each cell, right? I'm scrolling down here. As you can see, we have benign, we have malignant, and these are the inputs, right? So the inputs are named, I mean, in Python, it's named automatically and numbered from 2 up till 31. Okay, unfortunately, but it's okay. So here we separate the data into inputs and target. This line is seeding our built-in random generator so that each time I run, I will get the same results. This is not needed for you. This is for teaching purposes only, for consistency. And this is where we do our training test split. That means we take our data, we split into training data and test data. And the ratio is 75-25, which means 75% of our data goes to training data, and the remaining 25% becomes our test data. So this is where we build our decision tree model. Here we predict the output. Here we build our k nearest neighbor model, and here we build our logistic regression model. In this part, I'm just putting everything in a nice display like this, and as you can see, these are the models that we have built: decision tree, k nearest neighbor, logistic regression. This is the evaluation accuracy, this is the validation accuracy. So once again, evaluation accuracy is a measure of performance of the model on the training data. Validation is the performance measure of the model on our test data. So if in particular, if we see decision tree, the accuracy is 1. The evaluation accuracy is 1. So this means that every output of our decision tree is correct compared to our training data. But don't be mistaken, this only happens for this particular split of our data set. All right, because I have seeded the random generator. If I did not have the seeding, each time I run this, I would have a different test train split, therefore different models, therefore different accuracy. Okay, so this is not always true. These results are true only for this particular splits of our data set. Okay, like I told you earlier in previous video, that we have to do these splits many times and build many models and get the average of the results of the performance measure, right? And that method is called cross validation. But for your syllabus, we did the split and the model building and evaluation and validation only once. So let's see here. Our validation accuracy is 0.90, and for k nearest neighbor, it's almost close. That means both evaluation and validation accuracy are close to each other. In actual application, we want these numbers to be as high as possible and as close as possible. So as I mentioned earlier, if the evaluation accuracy is very high and the validation accuracy becomes, let's say if you get 0.7 or 0. Even 0.8, that means there have been some amount of overfitting. So we don't want our model to overfit. We don't want our model to memorize our training data. We want our model or models to learn the pattern or the trend in our data set. So for this particular split, the best model is our logistic regression model, because we can see the number is the highest, the accuracy is the highest, 0.95, and they are very similar to each other. So this is an evidence that we have minimum overfitting. All right, let's see how our decision tree looks like. So I've shown you how you can produce the figure. I've pasted it here. So this is how our decision tree looks like. Because our data set, this is our data set, some portion of our data set, because the columns are named using numbers. So we have numbers here, unfortunately. So in order to produce a prediction or an output from our decision tree, we have to start from the root node up till the leaf nodes. So these are the leaf nodes, right, where it ends. So for example, if we take a snippet of our data set, in particular we have about 5 here, and we have all inputs only. So from column 2 till column 31 are our inputs. So what is the predicted output? Let's see, let's check for row number 1, right? So if we have a new inputs like this in row number 1, let's see what our decision tree produces the output as. So the first decision, we have to look at column number 9. This is column number 9. Is it less or equal than 0? The answer is no. So we have to go here. Next, we have to look at column 25. Is it less or equal than 785? So this is column 25. Is it less? Yes. So we go here. Next, column 23. Is it less than 23.7? The answer is no. So we go here. Next, we have to check column 28. Is it less than 0.4? Is it less than 0.4? The answer is no. So we go here. So therefore, the prediction or the output is malignant for row number 1. How about row number 2? Again, this is row number 2. I hope you can see my cursor. Is it less or equal than 0? The answer is no. So we go to right. Now let's check 25. Is it less or equal than 785? The answer is yes. So we go to the left here. Next, look at 23. Is it less than 23.7? The answer is no, because here is 25.78. We have to go to the right. Next, check 28. Is it less or equal than 0.4? Yes. So the answer is benign. All right. Similarly, you can test for the rest of the data set. So basically, that is how we produce outputs from our decision tree. Now let's look at another example. So I've extracted some portion of our data set, in particular column 9 and column 25. All right, and I've extracted only about 10 rows of data. Okay, and let's see how we can build a k nearest neighbor model. All right, so as you know, the first step, assuming this is our complete data set, which is not, but for the sake of explanation, let's assume that we have many columns, right? But for some reason we decided that we are going to look at only column 9 and 25, and we only have 10 rows of data. So first step, we have to split randomly. 70% becomes our training data and 30% becomes our test data. Using our training data, we have to build a k nearest neighbor model. So how do we do that? So if we plot the data set, we have this, right? And I've colored the markers red for malignant and blue for, benign as green. So let's see, 0.106, 0.106 should be somewhere here, and 1321 is here. So this is the first row. How about the second row? 0.03, 0.03 should be somewhere here, and 1030, this is also malignant. Second row. Third row, 0.02 and 506, so this is benign. Third row. So how do we actually build a model? So in short, this is the model. And next question is, how do we produce an output of our k nearest neighbor model? So let's see how we can do that. First step, model evaluation, which means we want to measure the performance of our model given the training data. So therefore, we have to generate prediction of our model for training data. So let's choose k equals to 3. So if you remember from our slides, the way we produce output is by looking at our neighbors. So if this is our new data, you look at 3 nearest neighbor. If we choose k to be 3, and we get the probability or the proportion of the classes. So in this case, we have 2/3 for blue class, and the probability that this data belongs to the orange class is 1/3. Because 1/3 is less than 2/3, we say that the new data belongs to the blue class. Right, so that is a simple recall. Now, so this is our training data from here. Okay, so now let's check for the first row, right? What should be the prediction? So I've plotted the first row of data as the black marker here. So we have to check our data with the existing points that we have here, right? These existing points, these are our training data, right? So if I have the black point now, which is the first row, what is the 3 nearest neighbor to the black point? So red, red, and red. So the probability that the black point belongs to the red class or malignant is 3/3. So therefore, the prediction is malignant. Let's look at second row of our data, of our training data. This is second row. And if we plot this, we get this black point. What are the 3 neighbors? Red, red, and red. So again, 3 over 3. So prediction is malignant. Let's look at third row. Third row, once again, if I plot this 0.022 and 506, I have this black point. Who are the three nearest neighbor? Green, green, and green. And now the probability that this black point belongs to the red class is 0. The probability that this black point belongs to the green class is 3 over 3. Therefore, it is benign. So similarly, you can do the same for the rest of the data in your training data set, and you can compute the accuracy, precision, or recall as you desire. So that is model evaluation. Now, model validation. For model validation, we have to generate outputs of our model given the test data. So this is test data. If you remember, it's from here. Test data, we have only 3. So, and still our existing plots here, this is our training data, similar as before. So we use the similar existing points from the beginning, which is our training data. Okay, so if I plot the first row 0.089 and 2145, I have this black point. We have to identify 3 nearest neighbor using distance, using our Euclidean distance. So we can see that the nearest distance will be most probably 1, 2, 3, right? So what is the proportion of red class? It's 3 over 3. What is the proportion or the probability that this point belongs to the green class? It's 0. Therefore, this has to be malignant. So the prediction is malignant. Next, second row. If I plot this, you get this. Identify 3 nearest neighbors. Obviously 1, 2, 3. So the prediction is benign. Third row, let's plot this. We have this, and 3 neighbors are 1, 2, 3, and our prediction is benign. So there we go. I hope you understand. Please prepare for some questions to ask me.